We're going to continue talking with section 3.2 in chapter 3. And we're going to focus on standard deviation of the residuals, R squared, which is your coefficient of determination, and looking at a computer output. So we have this thing, we talked about residuals last class, and residuals measure the difference between the actual Y value and the predicted value. Then we have this thing called the standard deviation of the residuals, which is S. So to assess how well the line fits all of the data, we need to consider the residuals for each observation, not just one individual one. So using these residuals, we can estimate the typical or the prediction error when using the least squares regression line. This is not a formula you need to memorize, okay? This is not something you need to memorize. The calculator can get this value for you, or you'll be given it and you'll just need to interpret it. This is what we refer to as the standard deviation of the residuals S. This value gives the approximate size of a typical prediction error, your residual, aka on average, or typically speaking, how far your actual Y value is from the predicted Y value from your regression model. Think about standard deviation in general. If we think about standard deviation, it's your typical or average distance from the mean. It's the same idea and concept here, except now we're talking about the typical or average distance your Y values, your observed are, from the predicted value from the regression line. So, as I've said, what is the standard deviation of the residuals? It gives the typical or average distance the observed or actual values are from those predicted by the LSRL, the least squares regression line. It's very, very, very rare that you'd have to calculate this. You won't have to do that. It is the standard deviation of the residual list. So when you're asked to interpret it, on average or typically, our predicted Y values, and use context there, by the LSRL are blank, whatever the standard deviation is, away from the actual Y values observed. So again, on average or typically, how far your Y values are from the predicted amount. So if we looked at example 1, back to your soda example, the standard deviation of the residuals is 5 milliliters. Interpret this value. So the predicted amount of soda remaining, which is our Y, is typically, or on average, 5.00 milliliters away from the actual amount remaining. So it tells you on average or typically how far away the observed is from the predicted. This next page gets a little bit abstract. I'm going to go through it, but if you don't fully understand it, it's okay. What we're shifting gears into is this other value called the coefficient of determination. So suppose we wandered during the can tapping experience and found a partially full can without measuring the contents. How could we tell how much soda is left? The best guess here would be the mean amount of soda remaining in the cans. Notice that we have a straight line here where it's the same amount with no difference based on the tapping amount. So if we only use the mean for our guesses, we would expect a lot of error, right? Because we do think that there is a relationship between tapping time and soda amount remaining. Using the mean line, saying it's going to be equal to, Y is equal to whatever your mean Y value is, the sum of the squared residuals, so the sum of all these squared residuals, is equal to 6506. The question then we can ask is, okay, to see how good our line is how much better would our predictions be if we knew how long the can had been tapped, which now clearly we do here. So in this case here, we can compare the sum of the squared residuals to our mean Y line. So now we're saying, okay, this is if we had no indication about tapping time, we would just use the mean Y value. Now we do. And what we want to do is we want to compare how much better this line is to this. So we're going to look at the ratio. The sum of the squared residuals here is 951.3. Remember, here is 6506. So if we take 951.3 and we divide it by 6506, we're going to get 0.146 or 14.6%. What does that mean? That means that only 14.6% of the possible variation in the remaining soda is unaccounted for by the least squares regression line, meaning that the remaining variation is due to other uncontrollable factors such as how vigorous the shake was, maybe there was a timing error, maybe there was a slightly different amount of soda in the can, all of those things. Therefore, if we take 1 minus that value, we're going to get 0.854 or 85.4%, meaning 85.4% of the variation in the soda amount remaining is accounted for by our least squares regression line. So this number that we've just kind of measured in here is really how much better this line is than the standard mean Y line would be. That might be a little bit abstract for you, and I might have lost you along the way, but I wanted to give you that foundation of what this value actually is. And this value is what's called R squared, or the coefficient of determination. So the coefficient of determination, R squared, is the proportion of variation in the values of Y that is accounted for by the least squares regression line of Y on X. Again, you do not need to understand this formula or know this formula or anything like that. R squared will be calculated on the calculator, but what it is what we just showed. It's the sum of the squares of the least squares regression line divided by the sum of the squares of the mean line Y. Okay, we do 1 minus that to get that value there. We had the standard deviation of the residuals, which predicts how well our line fits the data. We also have this coefficient of determination. The closer this coefficient of determination is to 1, the better the line fits the data. So, as I said, the coefficient of determination tells us how much better our least squares regression line is in making predictions than if we were just to use the mean Y value for all of our guesses. We have the formula above, but you're going to be using the calculator. When we go to linear regression, under stat and calc, and either number 4 or number 8, as long as your diagnostic is on, your R squared value will always pop up. Interpreting R squared is something you do need to memorize, and this formula is something that you need to kind of have in the back of your head. It represents the percent of the variation in your Y variable, and whatever that is, use context, that can be accounted for by the least squares regression line. R squared is obviously related to R. R is equal to the square root of R squared. Be careful though, R can be either positive or negative, so it's important for you to look at the scatter plot or the slope of the regression line to determine the sign. R squared will always be positive, obviously, because you're squaring something. How is R squared related to S? Both measure how well the least squares regression line models the data. R squared does not have any units, while S is measured in the same units as the response variable Y. The smaller the S is, the closer R squared is going to be to 1. So they kind of have an inverse relationship there. Because if your S is really, really small, meaning your residuals are really low, then your line is going to fit the data really well, and your R squared value is going to be close to 1. So they have that inverse relationship. Let's take a look at this example here. This example measures the relationship between sprint time and long jump distance, which we saw earlier in section 3.1. They've given to us here the least squares regression line, Y hat, so your predicted long jump, is equal to 414.79 minus 45.74x, where x is the sprint. And they've also shown us the residual plot. They've given us S, which is 22.38, and they've given us R squared, which is 0.702. Notice there's no pattern in the residual plot, so a linear model is appropriate. It appears to have a strong negative linear correlation. Okay, if we wanted to take R, which we will, we can get that value there. So calculate the interpret the residual for Christian, who had a sprint time of 7.25 seconds and a long jump of 110 inches. So in order to calculate the residual, we need to take the actual, which is 110, minus the predicted. So we need to start by finding his predicted long jump distance. So we're going to take 7.25 and just plug it in for x into our regression model. 414.79 minus 45.74 times 7.25 will get you 83.175. So his predicted long jump distance is 83.175. And if you look at 7.25, which is right here, that does look about right based on our regression model. So now to find the residual, we take the actual A minus the predicted P, AP. 110 minus 83.175 will get you 26.825. So he has a positive residual, which he does. Oh, he's this guy. My bad, I think. Yeah, it's this guy. So Christian's actual long jump distance was 26.825 inches more his actual, than the predicted one by the regression line. So notice that he's above. So his actual long jump distance was 26.825 inches more than the long jump predicted by the least squares regression line. Notice I've used context, talking about long jump distance. I've used direction more than, okay? Make sure that you're including all of that in your interpretation of a residual. Part B, is a linear model appropriate? Yes. Why? Because there's no obvious pattern in our residual plot. My residual plot shows no pattern. It's fully scattered about. Therefore, there is a linear model is appropriate. Now we're asked to interpret S. Remember, S is your typical distance your observed are from your predicted. Let's throw some context on there. So on average, or typically, the predicted long jump distance differs from the actual long jump distance by 22.38 inches. So basically what I'm saying is on average, how far away these actual ones are from the predicted. That's all you're really doing when you're interpreting the standard deviation of the residuals. R squared is 0.702. What does that mean? It means 70.2% of the variation in long jump distance is accounted for by the least squares regression line. We're just using that basic interpretation sentence that we saw earlier. And last part here in E, find the coefficient or the correlation coefficient R. So if we have R squared at 0.702, to find R, I need to take the square root. Notice that it's a negative R value here. Okay, if you just take the square root of 0.702, you're going to get 0.838. But I can see from two things. A, my slope is negative. So if the slope is negative, I know that my points have to be going down from left to right, and R has to be negative. And I noticed by just looking at the scatter plot that it has a negative correlation. So my R value here is going to be negative. It is negative 0.838, which means there's a strong negative linear association between our two variables here. And I knew it was negative by both looking at the scatter plot or the slope. We'll save this next example for class. Let's move on here to interpreting a computer regression output. AP exam loves to show these computer regression outputs. There's lots of different statistics software out there that will give you this stuff. There's Minitab, there's Fathom, there's a couple other ones that can give you these values here. So they often will give you something that looks like this, and we need to be able to pick out the important things that are involved in here. Almost always there will be something that's called your constant or your intercept. That's going to be your Y-intercept, which is right here. The other value here is your slope. We don't care about anything that's in this part in here. So we only care about these two coefficients, which is where you'll get your Y-intercept and your slope from. So make sure in your notes you're labeling these. There's another thing called R square adjusted. We don't care about that either. So far we don't care about anything that's on the right side in here. We care about this value in here, S, which is your standard deviation of the residuals, and R-SQ is your R squared value, your coefficient of determination. So the constant is your Y-intercept. The points per game in this case, or your other thing here, is your slope. And then you've got your standard deviation of your residuals and your R squared, your coefficient of determination. So if we look at another example, slightly different thing, different setup here, but it tells us all the same basic stuff. Again, we don't care about all this nonsense in here. This one actually tells you the intercept, okay? So this would be our Y-intercept. The other value here is your slope. Again, we don't care about R squared adjusted. And this one they call the root mean square error. That's your standard deviation of your residuals as well. So just another different computer output for you to look at. Just make sure you're able to pick out the important things. Your constant or your intercept is always going to be your Y-intercept. The other value, which is either going to be referred to as your estimate or your coefficient, is your slope. And then be able to find the R squared and the standard deviation of the residuals, which will be included in any computer output. There's an example that follows here, which we'll do in class. This next page, if you want to look at it on your own, feel free to look at it on your own. It goes about how to go about finding the slope and the Y-intercept by hand. It's included in the notes that I've posted on Classroom, but I'm not going to spend any time going through it during the video or in class. So let's put it all together here and talk about everything that we've kind of encompassed in this chapter, which is a lot. First of all, correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, be aware of their limitations. So there's a couple things that we have to be cautious and know about. First thing is that the distinction between the explanatory and the response variables is important. Here, if we think back to that truck example where we're looking at the miles driven and the price, we switch the y and x variables here. So notice here, x is miles driven, y is price, and here we switch them. When you're doing that, certain things change and certain things do not change, okay? If we look here, our r squared value does not change. So r and r squared is not going to change. Your regression lines clearly are different here, okay? And your S, your standard deviations of the residuals also change. So r and r squared are going to be the same because they have no unit. So they make no distinction between the explanatory and the response variable. If you switch your x and your y, though, the slope is going to change, the y-intercept is going to change, and your standard deviation S is going to change. So does it matter which variable is x and which is y? It does for the slope, for the least squares regression line, your slope, your y-intercept, and the standard deviation of the residuals. It does not matter for the correlation r or r squared. Correlation and regression describe the linear relationship between your two variables. So we have 4 scatter plots in here, all very different, right? This looks like a typical linear-ish one. This has a obviously almost parabolic shape. This one is like a straight line except for this one massive outlier or influential point. Same idea here. This is almost a perfect straight line except for this outlier. Well, if you were to find the R value for all of these sets of data, it actually is the same. They all have an R value equal to 0.81. So what does that mean? It means that R tells you nothing about the form, only the direction and the strength of the relationship, which means it's always important to not look at just R singularly. You want to look at your data, plot the data on a scatter plot before you do any calculations, before you find the R squared, the least squares regression line. R is just a supplement, and it does not tell the whole story, okay? You want to look at the trend in the scatter plot first, and then go ahead, find the least squares regression line, find R, find S, find R squared. But don't just look at an R value and think that you'll know exactly what the shape of the scatter plot is going to be, what the form is going to be. You need to plot your data. You need to look at the graph of the data when you're looking at any regression or linear model situation. Third major thing, correlation and least squares regression lines are not resistant. So here's a scatter plot that shows the cost in dollars and the battery life in hours for a sample of notebooks or small laptop computers. What effect do the 2 netbooks that cost $500, these guys in here, have on the equation of the least squares regression line? So the dark line that you see here is the least squares regression line with these 2 influential points. Notice that if we've eliminated these 2, so if I got rid of these guys here, and I just looked at this, what I've drawn in here is your least squares regression line, not including those 2 points. Notice that there appears to be a strong positive correlation here between cost and battery life. But if I include those 2 guys, the dark line that you see here is the least squares regression line with those 2 influential points. So these 2 influential points, they decrease the slope, they increase the y-intercept, they're increasing the standard deviation of the residuals, they're decreasing R squared, right? Because the line is not as good of a fit, and they're decreasing the absolute value of R. We went from what would have been a positive correlation, that's pretty strong, to almost no correlation, that's slightly negative. So outliers and influential observations in regression. The least squares line makes the sum of the squared residuals as small as possible. A point that is extreme in the x direction with no other points near it will pull the line towards itself. That is what's referred to as an influential point. So these are influential points. They're pulling this regression line from what was my dotted line without them all the way down towards them, making them influential points. They are outliers in they're extremes in the x direction, which are pulling my line in that particular case. An outlier, just an outlier, is an observation that lies outside the overall pattern of the other observation. It becomes influential if it's markedly changing the result of the calculation for our least squares regression line. Points that are outliers in the y direction but not the x direction of a scatter plot have large residuals. Other outliers may not necessarily have large residuals. Points that are outliers in the x direction, which is what we just saw, are influential points. So how do outliers affect the correlation, the least squares regression line, and the standard deviation of the residuals? They're going to decrease the R value. They're going to pull the least squares regression line in the direction of those outliers. And they're going to increase S since there's more variability. All outliers are not necessarily influential. For example, vertically stacked, meaning above or below the X mean, have little influence on the least squares regression line. Outliers far from the X mean are influential. What that means is when we have an X, or we have outliers that are really far away in the X direction, they become influential points. And finally, and perhaps most importantly, association does not imply causation. So association and correlation does not mean causation. An association between an explanatory variable x and response variable y, even if it is very strong, is not itself good evidence in x actually causing changes in y's. And we will look at a case in the notes that deal with that. Final page in chapter 3 is on page 27. We'll go through these common misinterpretations in class. You can take a peek at those and some AP exam tips beforehand. I know there was a lot. This is an important chapter. I will see you in class.